Good afternoon, colleagues. Welcome again to this technical session. I would like to kindly request that all participants turn off their video cameras so we can take advantage of the internet bandwidth for the presentation, and also to turn off your microphones. It gives me a great pleasure to welcome you again to this afternoon technical session. Mr. Fumi, could I ask you to turn off your camera, please?
Yes.
So, good afternoon, colleagues. It gives me a pleasure to welcome you to this technical segment, where we would like to present a little bit of the step-by-step procedures and information contained in the UN Spider Knowledge Portal, and to also make websites and portals that host satellite imagery. This session will be managed by my colleague Radu Botes, who oversees all of the content of the Knowledge Portal and works with us in the provision of technical advisory support to Africa and other countries. Radu, the floor is yours, please.
Thanks, Juan Carlos, and welcome everyone to this more technical session. We will, as Juan Carlos mentioned, speak about the UN Spider recommended practices related to flood, and we will later on also speak a bit about the UN Spider Knowledge Portal more generally, as well as about some web-based systems and how to actually combine these different sources. For this first presentation, I would like to introduce my colleagues Ingrid Wong and Victor Hertel, who will take over some parts of the presentation. You should now be seeing the slides on your screen, hopefully. And yeah, we will follow the following outline. We will start by providing an overview of UN Spider recommended practices related to flood. We'll move on to the ones on flood hazard mapping or related to flood hazard mapping. And then we'll look more at the emergency response part, and we'll walk you through what we have on using STAR data, so radar data for flood mapping. If I could ask, thank you, everyone to mute their microphones and ideally turn off the camera so that we also don't have issues with the screen share. It might be at times a bit, not as smoothly as you expect on the screen share. That's because things are delayed and we're in different locations, and Microsoft Teams, of course, has to keep up with all of that. So do let us know if there are any major issues that you're facing, and we'll try to find a solution to that. We will go through slides now, but we will share our screens later on to basically provide a live demo of the different products and tools. If you have questions, feel free to put them in the chat. We'll try to address them during the presentation to the extent possible. We will then also take some questions after the presentations. It's not really a hands-on session in the sense that it might be a bit too fast to follow along. What we would like to do with this session is really provide an overview of what's available, what we are typically working on and developing at UN Spider, what's also available from partners and other institutions. Of course, you've heard about GLOFASS this morning, and we will also briefly mention GLOFASS as well as other systems such as the Global Drought Observatory, which is also more on the drought mapping part. So we'll also speak a bit about drought towards the end of this session. All right, so just to set the scene a bit, and you've seen this chart earlier today, I believe, or actually yesterday. What we're looking at UN Spider are all phases of the disaster management cycle. So we're not only looking at mapping after the disaster, but we're also looking at the prevention and mitigation phase, at preparedness, so that indeed we support stakeholders with using space-based information and space technologies in all phases of the disaster management cycle. And our capacity building efforts are addressing all phases, not only the response phase. So just to underline that. The products or the step-by-step procedures you will see today or this afternoon, the so-called recommended practices address different phases of the disaster management cycle. So we will start with those that are looking more at this side, so on the prevention and mitigation part before a disaster happens. You have seen earlier today the presentation about the pilot project involving GLOFAS, which of course is supporting through the early warning element, preparedness. And then during this presentation now, we'll also speak about the response phase. The idea here being that space-based information obtained through remote sensing and Earth observation can indeed support all these phases of the disaster management cycle. And that's something to keep in mind also as we are all strengthening efforts on disaster risk reduction, which of course is outlined in the Sendai framework for disaster risk reduction that was adopted in 2015. So I think that's also something that is important to underline here. Space-based information is also feeding into that. Okay, so I will now pass over to my colleague Ingrid, and she will walk you through the recommended practices we have available on the knowledge portal related to the early phases of the disaster management cycle. And I see one camera on from Mr. Babatunde Oyo from NISA. If you could turn that off, that would be great, just to make sure that we have enough bandwidth for the presentation. Okay, I will now pass over to Ingrid. Ingrid, just let me know when to switch slides. I will do that from this end.
Great, thanks, Radu. So, yep, we can switch to the next slide. So yes, so for the suggested workflow for the flood hazard mapping, so it consists of first step, flood hazard extent generation using space data of past event or through hydrological modeling or retrieving data from archived databases. And the second step is through exposure analysis. Sorry, yeah, okay, great. So the second step is through exposure analysis in GIS using supporting data. And the third step is map creation. And now I will go further into each step in the next slides. So first, for flood hazard extent or the flood mask layer, it shows the extent of a historical flood or potential flood. And flood hazard extents are often generated through space data of past event or through hydrological modeling. And as you can see on the right, the image shows an example of a flood mask layer generated using Sentinel-1 radar imagery over Lokoja and nearby area during the flood in October 2020. And it is important to archive newly generated flood mask into databases because flood hazard extents can also be retrieved through database of past flood events, modeled events, and also calculated flood return periods. Next slide. For flood hazard extent generation, UN Spider has several recommended practices that provide step-by-step workflows using publicly available Sentinel-1 data and free software for processing, as well as workflows using free software that conducts flood hazard modeling. The outputs of the recommended practices are flood masks in vector or raster formats that can be opened with GIS software to produce hazard maps or for further analysis. And as mentioned before, it is good practice to build up database for generated flood hazard extents for future use. Next slide. So after deriving the flood hazard extent, the impact of the flood hazard could then be estimated and mapped by overlaying exposed elements in GIS software. And this process is called exposure analysis. The exposed elements are auxiliary data such as population, land cover, infrastructures such as buildings and roads, critical infrastructures such as power lines and hospitals, and other points of interest. Next slide. And UN Spider also has workflows for exposure analysis using free software and free data sources. Next, I will do a quick demonstration of the exposure mapping recommended practice for population, land cover, and infrastructures as exposed elements, which is the first one there. And I will also share my screen now. And here we go. Yes, so here. Yep, so now I will do a quick demonstration of the exposure mapping recommended practice. And I'm sharing my screen here with my QGIS project open. And I'm using QGIS version 3.18. The area of interest, here you can see, is along the Niger River near Lokoja. And to get this started, you can see on the left here, I've imported all the required data into the project. So we have flood hazard extent, and there's gridded population. I can turn on here. And I've also have land cover and infrastructure, as you can see here, and also administrative boundaries. And I will go through the analysis one by one. So the flood mass layer here is a shapefile generated through Sentinel-1 data on October 11, 2020, using Google Earth Engine, which Radu will demonstrate later. And using the LGA boundaries from the Database of Global Administrative Areas, GADM, and it is a free publicly available data source. And I've split the flood mask into 4 polygon groups according to the LGAs that they're located in for further analysis. And the Nigeria 2020 gridded population data, here you can see in red, is from WorldPop with a 100 square meter resolution. And to get the total population that could be affected by the flood, and you can simply use a tool called Zonal Statistics. And when you input the flood mask in, and then the raster layer with the population per hectare, and then with the output column as population, I abbreviated it with POP, and then just do a quick sum, which is the total. And then quickly there, I will be able to see in the attribute table the total population, estimated population that could be affected within each LGA. And here's the number, total number, based on the population data. So next I'll go through land cover, which, as you can see here, the land cover raster data is a 20-meter resolution from ESA. They developed a land cover map of Africa using Sentinel-2 data for the entire year of 2016. And this is a really fine resolution and only for Africa. So to get the area of affected land cover type, I will extract the raster pixels that fall within the flood mask. And for time's sake, I have already the extracted layer here, as you can see. And then afterwards, I will use a tool called Unique Values Report on the extracted layer. Here it is, and for time's sake as well, I also ran the tool already, and then in the Unique Values table, then you can see, according to each land cover type, you will be able to see the meter squared that is affected. And you can do further calculation to kilometer squared or make it look better. Yeah. So, yep, as you can see, the results are here, and that would be the land cover analysis. And also using different symbologies, you can actually just extract the croplands or built up areas for visualization purposes. And yes, that's for the land cover analysis. And lastly, I would also show you for buildings and roads. And I would also have to zoom into a closer area. And here we go. So I've zoomed in now to an area called Edeha, I believe. Yes, Edeha. And so this is a very tiny settlement that's north of Lokoja, and the roads and buildings data are from the Humanitarian OpenStreetMap team, which the data could actually be imported straight into QGIS through a plugin called Quick OSM. And the healthcare, and I also have here, you can see I have a healthcare facilities location data here as well, and also the settlement names here. And these data, I've obtained them from the Grid 3 Nigeria database. So due to the large amount of polygons, lines, and points that could be generated, I would recommend to conduct this kind of analysis for a smaller, more local scale. And so to locate the infrastructures and points of interest that could be flooded, simply use a tool called intersection. And there you can import the buildings and then overlay by the flooded area. And once you run it, you will actually see the yellow areas, which are the identified areas that could be flooded by through this intersection analysis. And a new shapefile, as you can see, will be created, and it points out where exactly they are. So here's my quick demonstration, and then I will go back to Radu's PowerPoint.
Ingrid, just let me ask participants if they have any questions.
Yep, no problem.
Does anybody have any questions about what she showed? I mean, Quantum GIS is an open software. Are there any questions or comments or suggestions from your side?
Okay.
Just a comment from my side. Sorry, go ahead. What's God's time?
God's time. I am very sure that those who are participating will want to have perhaps the step-by-step these flooded areas demonstration that has done. Is this included in the recommended practices and how they get the link? Exposure mapping.
Yep, so this exposure mapping is a recommended practices, and there are step-by-step procedures, and you can see on the PowerPoint sharing here the first link, exposure mapping, it is included in the slide. So I believe it will go along with the uploaded presentation. Radu, you can correct me if I'm wrong.
No, that will go up. And I see a comment in the chat saying this was fast. Indeed, it was fast. And the idea here is a bit to say what's available. All these steps I explained really step by step on the knowledge portal. We will include links. We will also show you in a bit how to get there. It's not really the objective to follow along. We know it's fast. The idea is to see what's available. What can I do with it in terms of, what's the output and the insights I might be able to generate. Also, the data sets that we have now included are for demonstration purposes. You will surely have some local data sets that you might want to use, which you know are just more adequate. That's, of course, something that can be used with the procedure. But the idea is to say we have a couple of these. This is what they might provide you, and they are available online. The step-by-steps are also available online, and we will share the links, of course.
Can I just say something? Hello?
Yes, Dr.
Yeah.
Please go ahead.
Yeah, thank you very much. I think the presentation is going on fine. Yeah, it could be fast, but I think if we have access to the recordings of this of the presentation, then a lot of questions can follow thereafter. It may not just be during this presentation. There must be follow-up kind of way of interacting. So I think the presentation is going on fine. What is important is to have access to the recordings. Thank you.
Yeah, we will make that accessible. So the one from the session yesterday is already online. We'll work on getting the recordings from today up as quickly as possible as well. All of this will be available. So for this, I would suggest, Ingrid, if you want to continue.
All right. Yep, so you can go on to the next slide. Yes, and the results from the exposure analysis demonstration that I just really quickly showed could then actually be exported as maps to support decision-making in the prevention and mitigation phase. And exposure maps are useful tools for decision makers, and they are used to provide visualization for locating the amount of people and targeted land cover that could be affected, for example, in the two maps that examples that I have here, and in order to allocate resources and make mitigation plans accordingly. And next slide.
Ingrid, I think we again have a question by Dr. Agbaje, or a comment. Dr. Agbaje?
Yes, please. Come again.
Do you want to make a comment or a question? I see your hand raised again.
Oh, no. Yeah, I raised it earlier on, but I'm sorry, I didn't remove it. I already made the comment.
All right, thank you.
Thank you.
All right, so, and as you can see here, exposure maps can be done at various scales, and depending on the resolution of the data that you have of your exposed elements, local scale maps, for example, for the one that I have here, are useful to target smaller local communities to better prepare for floods. And this map here not only shows the buildings and roads that could be flooded, but it also shows the location of healthcare facilities that not only is important to know when disaster hits, but it's also important to analyze if they are exposed, so appropriate measures could be taken. So, yep, next slide.
Yeah, thanks, Ingrid. So now we'll move a bit on in the disaster management cycle. So we move to the disaster and response phase of the cycle, and we have a few recommended practices there. On the portal, of course, there are a few more than those we're showing today. We're just showing a selection. The next recommended practices will use satellite, so radar satellite data to be precise, to map the flood extent after a flood occurs. One of these recommended practices also allows to calculate an estimate of the land cover and population affected, just like we did in QGIS, except that it's doing that in Google Earth Engine. So the first one, the radar-based flood mapping, has two versions. There's a version that uses the freely accessible software SNAP, which has been developed by the European Space Agency. This version that we're presenting now is using Python. The reason for this being that the way it was structured, and Victor will speak about that, allows it to be run in the cloud. So we're looking here at basically providing users the ability to quickly execute a script and get results. But Victor will go into detail on these things. So I'm passing on the floor to Victor.
All right, thanks Radu, and hello everyone. It's a pleasure to meet you. My name is Victor, and I'm happy to show you a little bit on what we're doing on radar-based flood mapping. I would like to start with a short introduction and summary of the relevant information on satellite remote sensing for flood mapping. And as you can see on this slide, there are basically two different types of sensors that we can use for flood mapping. We have passive sensors on the left side, and as shown in the animation, passive sensors do passively detect signals that are reflected from the Earth's surface or signals which were emitted by the Earth itself. And on the right side, we have an active sensor, and active sensors, as shown in the animation again, to actively send out a signal and detect the echo, so the portion of the signal which is reflected from the Earth's surface. And one of the most active satellite sensors is called synthetic aperture radar, or in short SAR. Now there are different advantages and disadvantages coming along with these two types of sensors. Maybe Radu, if you could go to the previous slide again, that would be great, thanks. So passive sensors are often easier to interpret because they often operate with visible light or in the visible spectrum, and our eyes are used to this. While active sensors such as SAR, radar, for example, are not so easy to interpret because they require pre-processing before we can really work with them. This being said, the more important and the decisive factor in this context is that passive optical sensors depend on weather and lightning conditions. So we cannot see through clouds, and we can only detect very few information during the night. And since floods are often associated with bad weather conditions, this is a very strong disadvantage. So on the other side, active sensors such as SAR, they can penetrate clouds, and since the sensor is actively sending out a signal, it is also independent of lightning. So that means we can do flood mapping even in the night and even if it's cloudy. And this is one of the major reasons why flood mapping is often done using radar. Next slide, please. Now, let's look at the different reflection types of our SAR signal. It's important here to mention that SAR sensors are always looking to the side, like you can see on the slide here, to improve the resolution. And on the left side, we have the so-called specular reflection, as you can see in the animation that occurs on smooth surfaces such as water. And you can see that the signal is reflected pretty much in one direction. While on the other side, we have the so-called diffuse reflection, which occurs on more rough surfaces such as soil, where the signal is kind of going into all directions. And in reality, we mostly have a mixture between both, but this is important to understand when doing flood mapping. When the surface of the Earth is flooded, we have a relatively smooth surface and our SAR signal is mostly reflected away. So the echo that we detect is very small, and therefore flooded areas appear rather dark in the image. While when the surface is not flooded and we have a more rough surface, the signal is reflected in, as you see, all kinds of directions, and the echo that we receive is stronger. So the rough surfaces appear brighter in the image because the echo or the backscatter is larger. So you can basically say that the brightness of each pixel in the image that we get corresponds to the strength of the echo that we receive. Next slide, please. And we can see here how that looks like in the image. As said before, flooded areas or permanent water bodies such as rivers appear rather dark, and other areas like fields or cities appear bright. So we already have a first idea of the areas that could be flooded. And the main task now is to create a so-called binary map, which contains only the information yes, water, or no, no water. So we want to have an image which is, for example, black where there's water and white where there's no water. And there are different approaches to do this. The one we're using here is so-called rule-based approach or threshold approach. And that means that we're looking at the diagram that you can see on the right side, which is based on the image on the left side. This diagram is called histogram, and it shows on the horizontal axis kind of the brightness level of each pixel, and on the vertical axis the number of pixels. So in the image, we see that most pixels appear pretty bright, and these correspond to the major peak in the diagram. But we also see some very dark pixels, and in the histogram, we see a small second peak in the darker area of the histogram. So we can basically say that all pixels belonging to the major peak are no water because they are bright, and the majority of pixels belonging to the smaller peak are water because they appear dark in the image. And what we can do now is simply looking for the minimum in between those two peaks and say everything here on the left is water and everything on the right is no water. And the minimum is indicated to this red vertical line in the diagram. And if we apply this to the image and make all pixels on the right side of the threshold white and all pixels of the left side black, then we obtain our flood mask, which you can see on the next slide, please. Right, and this is already our final product, the flood mask. So we process the SAR data, then we look at the histogram to determine a proper threshold, the minimum, to distinguish between water and not water pixels, just based on the brightness level of the pixel in the image. And it's important here to mention that the threshold is not constant, so we'll have to look at this for each image individually. Next slide, please. Now, there's one disadvantage in this approach that is important to be aware of. So what you can see on the left side is a flooded urban area. And what you can see in the animation is that we have multiple reflections due to the urban geometries. So even though the area is flooded, we receive a strong echo, which means a bright image. And the same also applies for flooded vegetation in the animation on the right side. So it's important to be aware of that floods in urban areas and flooded vegetation are challenging objects for this approach, since we receive a strong echo where we would expect a weak echo. And this phenomenon is called double bounce backscatter because we have multiple reflections. Next slide, please. Okay, now coming to the platform and the data that we would like to demonstrate today. Maybe some of you already know what a Jupyter Notebook is. So a Jupyter Notebook is an interactive web application that includes text, visualization, and software code. And you can see in the GIF on the right side how that looks like. It's a comparably new platform that is very well suited for these kinds of applications because the mixture of text and code allows you to kind of follow these step-by-step procedures or recommended practices. But we'll have a look at this in a second. And the data that we're using comes from the Sentinel-1 satellites, which is a SAR mission of the Copernicus program of the European Union. And we're only using open access data, so everything is freely available. Next slide, please. And right, one of the advantages of using Jupyter Notebooks is, like Radu mentioned, that we can run them in cloud environments. So we've heard about that already in previous sessions, but the basic idea is just to use external resources for all the processing and downloading. So we can run the tool in the browser of a laptop, a smartphone, tablet, and just enter the input information, like the date, for example. Then the downloading and the processing is done in the cloud, and what we download to our local device is just the final product, so our flood mask. Okay, so far regarding the introduction, I would now like to give you a short demonstration on how such a Jupyter Notebook looks like and how it works. And for this, I will share my screen. Can you see the screen?
Yes.
Okay, perfect. So what we have here is the website of this recommended practice on the knowledge portal. And at the top, you can see 3 buttons. The first one brings you to a website where you can find an introduction and all necessary information and files, while the other 2 buttons below directly open the notebook in 2 different cloud environments. So the first one is called Binder, which is an open source server where you can directly run Jupyter Notebooks without any login details. And the second one is Google Colab, which is also a powerful cloud environment for Jupyter Notebooks. So I'm going to click the button and it opens the notebook. And at the beginning, you can find some introductory information, some resources, information on the workflow limitations, and so on. And the first thing that needs to be done is the initialization. And when doing this the very first time, it will take a few minutes to install and configure all required packages. So to save some time, I will switch to the same notebook where I already clicked on initialization. So here we go, same notebook. Just click again, initialization. It should be going quite fast. So the next thing to do is the user input, where you can define some parameters and indicate if you want to download an image or if you already have one. I will leave everything as it is and click on Run. Okay, in the next step, we are downloading an image directly in the Jupyter Notebook. So for doing so, we need to enter our username and our password to access the Copernicus Open Access Hub. And we need to enter the start and stop date of the period that we are looking for. So in this case, we're looking for images in between the 1st and the 14th of October in 2020. Now click on Run. and we get an interactive map where we have the opportunity to either manually draw our area of interest using the drawing tool here on the left side, or we can also upload a file including our area of interest using this upload dialog. We'll use this now. And now it's connecting to the Copernicus Open Access Hub and searching for available Sentinel-1 images, given our indicated period and area of interest. So we can see it found one image that was taken on the 11th of October. And below it shows a table where we can directly download the image inside of the notebook. In case there would be several images, we would see several images here and a longer table with multiple images to download. And again, to save some time, I downloaded this image already prior to this presentation, so we can directly go to the next part, the processing. And since this will take a minute or two, I will click on Run already. And now I want to quickly go through the processing steps. So it's not mandatory to understand them in detail, but if you're interested, there's some explanation text in the notebook, and there's plenty of literature regarding each processing step. So in the first step, apply orbit file, where we basically update the position and velocity information of the satellite when the image was taken. Afterwards, we do some thermal noise removal. Then the third step, radiometric calibration, is one of the most important SAR processing steps because it kind of correlates the image to numbers that we can calculate with. Then afterwards, we apply a speckle filter, which kind of smooths the image a little bit. In the next step, due to the side-looking geometry of the SAR sensor, as I mentioned in the presentation, the terrain in the image is a bit distorted. So in step 5, we correct this distortion. And then in step 6, we do the binarization, which is what I explained in the presentation, where we look at the histogram of the image to distinguish between water and no water to obtain our flood mask. And finally, we do a speckle filter again. So since we are only interested in the region we defined above, a subset was taken according to this area, because this saves up time and processing resources, because we don't need to process the whole image. And then you can see here all the processing steps that we just discussed: the thermal noise removal, calibration, speckle filtering, terrain correction. It's now still taking some time to do the plots to see if everything worked correctly. Should see the image by now. So this is the processed image and the corresponding histogram with a threshold that is automatically calculated. All right, and in the last step, we export the data such that we can use it for exposure mapping, for example, like Ingrid showed before. And it is being exported in 4 different formats, which are GeoTIFF, shapefiles, KML, and GeoJSON. And while this is exporting, I would like to show you where you can find these results. So as this platform is Google Colab is linked to Google, the results can be found in the Google Drive. So I opened here the Google Drive. Here's the Jupyter Notebook. And during the processing, it created this folder radar-based flood mapping. Go inside, we find the subfolders, the input. This is where we save the input Sentinel-1 image that we've downloaded. Then the area of interest, AOI subfolder. This is either saves the area of interest that we have manually drawn or the one that we have uploaded. In this case, the one that I uploaded. And then in the output folder, it stores all the different output formats. So GeoTIFF, GeoJSON, KML, and shapefile that we can then download and further do analysis with in other softwares. So this will take also about 2 minutes. In the meanwhile, I wanted to show you how this output data looks in different softwares. As you have seen in Ingrid's presentation, you can visualize them in QGIS. which is one of the most common open source geographic information systems. Can do further analysis here, like the exposure mapping. But you could also visualize the KML files, for example, in Google Earth Pro, which also gives a good overview of the situation. And going back to the Jupyter Notebook, we'll just wait for a few more seconds until that's done.
Victor, maybe you could briefly speak about the resources this is using or not using actually. So as you mentioned, the data is downloaded on your Google Drive, which means it will not download on your computer. We see in the upper right-hand corner the RAM. Can you maybe walk us a bit through how behind the scenes this is dealing with the usually very large amount of Sentinel data, which, as we have seen, would have been a gigabyte in this case?
Right. So as I mentioned, this is running on in a cloud environment. So what we basically do is we just click on run, and all the processing, all the downloading is happening in the cloud. You can see these, in the case of Google Colab, you can see here the resources that are available. So you have the numbers, 12 gigabytes of RAM and about 100 gigabytes to store data. You can also directly save images like we do the final outcomes in your Google in your Drive. This is for Google Colab. Again, there's this other environment called Binder, which is open source, which offers 2 or sometimes 8 gigabytes of RAM, which is also sufficient. And it saves, as Radu said, quite some bandwidth, as we don't have to download gigabytes of Sentinel-1 images. One Sentinel-1 image that we're using is normally about 1 gigabyte or 2. And the output that we are downloading is just in the range of kilobytes or megabytes. So instead of downloading the whole image of a gigabyte or more, we only need to download the outcome, the flood mask, in vector or raster format, which is in the range of megabytes. And right, this is pretty much the major advantage of running this notebook in the cloud, because we only kind of operate and click on run and input our input data with the user inputs, and all the high-level processing and downloading is not happening on the local machine. And right after, once the export is done, it shows the path where it's saved, and also another interactive map where you can also visualize the outcome and play around with the different layers, also at the satellite layer to get a better idea of the areas that are flooded. And yeah, that's basically it from my side. If you have any questions or any suggestions on how to improve this tool, of course, feel free to contact me or us. And yeah, thanks a lot for your attention, and I would give the floor back to Radu.
Thanks, Victor. This is, of course, really interesting, and indeed the ability to run this in the cloud so that local resources are not used is obviously very useful. One other point to underline here is that we are directly connecting to the basically the database of the Sentinel imageries, the Copernicus Open Sci-Hub, through the script. So there's no need to go to the page, get the data from the page. All of that is done through an API. So programmatically, the script will get the data from there, which again is saving one step, and has the advantage that once the data becomes available, you can use it with the script. So there's no delay between the data becoming available and us being able to use it with this script. Are there any questions at this stage for Victor before we move on to Google Earth Engine?
Okay, this is God's time. Mine is not a question, it's a comment, which I made yesterday also. The fact that one of the challenges we do have is the challenge of internet bandwidth. And so it was a major challenge in the past to download heavy satellite imageries, and this is a welcome development. This was the same platform that last year mapped the mask flooded area in Niger. This is a welcome development, and for participants, the challenge of poor bandwidth and not being able to satellite imagery. There are processing facilities cloud that can be used. Processing of your available, and the only thing that you actually download to your system is the final product. That is the final mask flooded areas. And like he mentioned, this may not be more than maybe maximum gigabyte, depending on the size. Yeah, that is. Thank you very much.
Thank you, Godstime. Is there any other comment or question? Of course, this we just showed basically the running of the script. So there's an entire Python script behind, which is extensively annotated for people with some experience in Python. If you're really interested to look at the script, that's of course also possible. We did not display the entire script now, but it's available. It's also available on GitHub. So all of this is as freely and openly accessible as possible. Also with the idea that, you know, if you want to take this further, then this is of course also possible, and we always try to annotate, to comment our scripts very extensively, so that there's also certain transparency about what we are doing and what the script is doing.
Yeah. Can I come in? I don't know. I
sure,
just
please,
want to make a
please
comment.
go ahead. Yeah.
Right. Well, thank you very much for the presentation. It's really interesting. What I usually say, coming from the educational institution, is domestication of all this knowledge, and trying to ensure that the students, and then the short courses which we normally give to workers, everything attuned to what they want. What is important is owing wherever it's been done. Yeah, we can have a lot of interface, but there'll be a lot of things behind it, which will ensure that our participants in our courses, they get the basic principles, so that it don't just become robots. Yeah, it makes the work faster, but there are some of them that we need to really ensure that capacity building is key. It's key in the sense that people don't just get used to clicking on buttons, and that's, they lost the basic principle, and they may not be able to even do some changes, or some using some other means to actually do the modeling, to actually get the solution. So it is important that this collaboration continues, and where you can really keep them in the educational institution and research institutions. For the people that are using them, they may not bother, but once they are there, student that passes through them, they'll be easy sources of using them, to employ them to actually continue with whatever they are doing with their mandates. That's I want to emphasize. It's not just them having to be clicking and then getting the buttons that is most important, so that the knowledge can stay there, can be enduring, can be domesticated, can be owned. That's just my comment. Thank you.
Yeah, thanks for that. Absolutely. I think indeed the need for capacity building, we have discussed that yesterday and today. That's of course very important. Indeed, this, yes, you can click on the buttons, but as you say, ideally this would be part of a larger curriculum. As you've seen, we also felt the need to basically provide at least a very, very short introduction to radar remote sensing before going into this, just to contextualize it. But of course, these could be building blocks of a curriculum eventually. One other point that I think is important, indeed, also when something breaks, I mean, these are platforms that are online and they are, the global platforms. For us, it was easy to use this, knowing that anyone could use it with a Google account. But of course, one question that still exists is, the need for more for platforms, cloud-based platforms that are indeed owned, be it at the national scale. So basically investment into cloud processing that also then is owned, because of course, these servers, they are somewhere, and eventually the company behind them might decide not to continue the service, which is a service that's provided for free. So there's always this risk associated with that. I see we have another hand up. From Idris.
Yeah. Good afternoon. Thank you for the presentation. I just want to ask Victor, when he was going through the Jupyter notebook process, there's some way they ask for username and password or something. So do I need to have an account with the Jupyter? Do I need to open an account on the platform or something for me to have access to that when I'm doing the processing?
Yeah, so you don't need an account that is related to the Jupyter project or anything, but you need to have an account for the Copernicus Open Access Hub, which is, the data provider. In either case, so in any way, if you want to download Sentinel images, Sentinel data, Sentinel 1, 2, 3, 5P or whatever, you need to be registered at the Copernicus Open Access Hub. This kind of allow you to access the data.
Thank you very much. Thank you.
Thanks.
All right. Any more questions? I see that Jibril DSA has the microphone on. I don't know if you have a question. No? Okay. All right, great. Yeah, so again, as for the previous one, this is available on Knowledge Portal, where you also have an extensive description of the process of the script, of how to run it. Of course, the script can also be downloaded. So if you are a bit more technical and you've worked with Python, you can of course just download the script. And if you have some other data, you could see how to adapt it. So that's of course also possible. All right, we will be moving on and we'll stay with the response phase. So I will share my screen again and we'll basically take you through another recommended practice, which is also using a cloud-based system. It's a different system. It's Google Earth Engine, not Google Colab. And this recommended practice allows users to indeed identify the flood extent, as well as to assess damage to a certain extent, as we also showed earlier in QGIS. So we'll get to the portal in a bit, just to say that this is what the page for this recommended practice looks like on the portal. All recommended practices will have a step-by-step explanation that goes through each step of processing. They will also have an in-detail page which is discussing advantages but also limitations. I think one element to underline, and that's of course important to keep in mind, is that we can certainly develop a lot of maps, but we need the ground truthing. We need to make sure that we check these things in real life, so to speak. So of course we can develop information products, but we should not forget that at the end of the day, these also need to basically undergo some verification and ideally be of course ground truthed. So that's something to keep in mind as we go through all these products. Let me now basically show you the workflow, and then I will go into Google Earth Engine and run this recommended practice. So as you can see, here we use a couple of data sources in this recommended practice, a few more than what we just saw on Jupyter Notebooks with Python. So we do use the same radar data, so it's Sentinel-1 data. We then use a digital elevation model to exclude certain areas that have a slope that's higher than 5%. We use the Global Surface Water Explorer data set for the Joint Research Center of the European Commission, so that we can exclude permanent waters in order to only basically have the flooded areas. We also use the Global Human Settlement layer, again from the Joint Research Center of the European Commission, which allows us then to analyze or estimate the population that's exposed and then, of course, potentially affected. We use MODIS land cover data to look at affected cropland and affected urban areas. So all these data sets are data sets that are available from the Google Earth Engine data catalog. They can be replaced. We did a training on this recommended practice last year, and one of the comments was that population data for Nigeria is maybe the one from World Pop is maybe more adequate, and there might be other data sets. So all of this can be replaced to a certain extent. This is what we have, and again, it's a global product, so to speak. So it's something that indeed we offer globally, and we make available for anyone to use. The idea being that users can then also bring it into their context, and I'll speak about those questions a bit later on. Right, let me just go through quickly the advantages and limitations. Some of them we've seen, but just to recap, so some of them are specific to radar data, others more to the platforms. We've heard that one advantage of radar data is that it's weather and data independent. That's indeed something that's makes it useful for this type of flood mapping. We have seen another advantage of these workflows in general, that it can be applied to different areas. Again, we always need the local knowledge to fully be able to develop insights. So we should not be necessarily misled by the idea that we just run this for our area, but the knowledge that will be available in the country, in your institutions, is crucial for this to be actually useful. Yes, you can click on these buttons and export the layer and so on, but only once you bring it into the context, the local context, the national context, combined with knowledge that is available in the different institutions, will this actually be really useful. This script, as the previous one, is fully automated. It's quick cloud processing, and it's easy to add additional data sets. In terms of limitations, the Google Earth Engine script that I will show is using change detection, and there might be change on land surfaces between the two moments in time that we will look at. So we will define a period before the floods and after the floods, and we'll use this change detection approach to identify the flooded area. There might be changes that are not caused by the flooding. We've seen the issue with difficulties of detecting floods in urban and densely vegetated areas. Depending on when the flood took place, we might not capture the flood peak, because these satellites, Sentinel-1, is not revisiting the area daily, but at a certain interval. And one point which I want to underline, compared to the previous recommended practice with Jupyter notebooks you have seen, is that data from the Sentinel satellite fleet, so including Sentinel-1, is available with a delay in the Google Earth Engine data catalog. So there's a delay of a couple of days, which means that we can run this, and as Ingrid was showing at the beginning, it might indeed help us also build our flood event database and add some historic information. But we need to be aware that if we want to use this for rapid mapping in the context of a disaster, it might be certainly more suitable to use the Jupyter notebook version that Victor just presented, because the data there, it will take the data from where the data is located as soon as it's available, whilst Google Earth Engine takes a couple of days to have the data in the system. So just to be aware of that. And of course, depending on the resolution of the different data sets, there might be some uncertainties for damage assessment. Sentinel-1 has a certain resolution. there will be other data sets with other resolutions. So that's a question to keep in mind. Okay, so we'll now go to the system, and I will basically show you how to access it, and we'll just run it. I'm just gonna look before I do that at the comments in the chat. Okay, great. So let's then move to Google Earth Engine again. You can access this with a Google account. You need to request access to Google Earth Engine, but that typically takes a maximum of a couple of days. And once you have that, you can access this code editor that looks like that. I have opened that up. So you now should be seeing indeed the Google Earth Engine code editor. I will just expand a certain part here. I'm not sure if there's a question or not. Okay, we'll just continue. All right, so this code editor is something that you can get to from the knowledge portal. So this is the page on the knowledge portal. Let me just try to have this correctly full screen. Okay. So this is the page on the knowledge portal. You find recommended practices under advisory support, recommended practices, and then you can click on the different ones. I'll show the knowledge portal a bit more extensively in a bit. And then here on step by step, once you click on that, you will get access to the step-by-step page. And that's, again, the same for all the recommended practices that we've shown today. And this will explain the process. So it will provide some background to what's actually happening. It will also provide the link to the script. It's also actually providing a link to where to sign up for Google Earth Engine if you don't have an account. But once you have that and you want to access the script, it is sufficient to click on this link, and that will open up the code editor. Again, there's a lot of context here, so you see all the steps involved. A lot of them are not necessarily manual. Some of them are. A lot is explanation, background information. But it's worthwhile reading through. And again, just to underline that the in detail page will have also the limitations, and it's important to be aware of the limitations as well. And there are a few for the scripts. We've seen those in Victor's part on radar remote sensing, but there are also others that are specific to Google Earth Engine, as I've just mentioned. Once you have the account and you have clicked on that link, you will get something like this. This is the Google Earth Engine code editor. I will run it for this area, but I just wanted to point out that you can also, if it's the first time you use Google Earth Engine, it's completely new to you. It looks like a lot of software code, and you can just run the demo that we have prepared. The demo is not an area of interest in Nigeria, but in Mozambique after Cyclone Idai in 2019. But this is something that you can run by simply removing those two slashes at the beginning of the script. And that's also explained here. So remove the comment symbol below, so Earth Engine recognizes the polygon. So that's when you first use it. I will not show you that. I will show you an area of interest in Nigeria. So I again look at the area around Lokoja, and to do that, to select an area of interest, there are a couple of options. We will use the drawing tool. I will actually remove what I have drawn before. So we will use the drawing tool, which allows us to select an area. So I'm drawing a rectangle, and I use this drawing tool. You can also draw other shapes, and you can upload. If you have a shapefile for an area of interest, you can also upload that. The process is explained on the knowledge portal in the step-by-step procedure. I have now drawn this, which means that the script is understanding this is my area of interest. So this is the geometry that I'm looking at, and it will use that geometry. So it will basically limit the data to that area, generally speaking. So this is also explained here, in case you would like to look that up later on. These things are commented in the script. We need to set a couple of other parameters. So we need to set the time frame, and we will set 2 time frames. One before the flood, ideally for a time when there are no floods, and then the one after. And as I said, this is using change detection, so it will look at before and after to determine the flooded areas. We will see the different layers in a bit. There are a couple of parameters that we need to define that are specific to radar remote sensing. So the polarization is one of them. We did not go into detail now. There are a number of materials online, but there are different polarizations, some which are preferred for flood mapping. Although you can here, I would suggest just try the different options. There are 2 options, VH and VV, and that relates to the way that basically the satellite is sensing the beam and receiving it. I will not go into detail, but you easily find literature about that. The other important element, and this is something that can be looked up, is the path direction of the satellite. So that's again something that we can change. It can be it's something that can be looked up. I'm just going to refer you to the step-by-step page, and I'm going to zoom to that section. Also to say that these questions, the parameters that need to be set, are explained here. So here, basically, we need to define the path direction of the satellite. There are 2 options: descending and ascending. Depending on the study area, it's one or both are available, and you can basically look up your area of interest. It will also indicate the frequency, the revisit frequency. And here we can see that this one is ascending. So if you want to look at areas of interest in Nigeria, we would set that parameter to ascending. If you set it
Rado?
Yeah.
Just a quick question, because I see that one participant is not able to see the screen anymore. Just wanted to ask everybody else if they're able to see the screen.
Yes, I'm seeing the screen from here.
Okay, all right.
I'm fine.
Yeah,
Okay.
I think we might have indeed here and there might be connection issues.
Sounds fine. Yeah.
Thanks very much. Sorry, Rado.
No worries. All right, so that's something we can indeed look up in the script, so that will explain what parameter that is and how to figure out how to set it. You can try setting them also to descending. You'll see what happens. There won't be any imagery. But again, it's worthwhile. I mean, these things you can change. The threshold is something that is basically selected by try and error. So this will try to figure out the flooded areas. So basically determining, okay, this is flooded, this is not flooded. And again, this ground truthing is critical, and knowing and basically having one of these products, comparing that with the situation on the ground, that's really important. We just want to underline that. Here we have a default threshold, but if indeed you feel that there are a lot of false positives or negative signals, you can change it. So you can indeed tweak that. Okay, so we've now selected the area of interest. We've set the dates. We can just simply run it and see what we get, and then I walk you through some of the issues and some of the elements that might pop up. So now I hit run, and this will basically start the process. Let me just expand that part a bit. so that you see what this is doing. If you want to, and I suggest you do that because it's just easier to see the rest, remove this box that you created for the area of interest. You just untick the geometry up here. So here you have, as in a GIS desktop tool, you have different layers. You can just untick that. So these are the geometry imports. You can also delete it by clicking on this setting wheel, and then you go on delete here, and this will remove the area of interest that you've defined. All right. So here we have a number of results. So if I zoom in, let me zoom in so that we can look at that specific area. We have a number of layers that we can also unselect if we don't want to see them, but let's just walk through all of them by starting with the before and after. So Google Earth Engine goes to the Google Earth Engine data catalog, is looking for imagery from Sentinel-1, and will select images for before, the period that we defined as the period before the floods and for the period after the floods. And these you can visualize here. So we could just basically, use the slider to change the transparency and basically overlay that. So we can see a bit of, darker areas here that might indicate flooding. It will then go on and create a difference layer. And based on that, so here we're in the logic of before, after, it will define potentially flooded areas. Then we have a number of other data sets I mentioned. So we have population density. This is the global human settlement layer from GRC that will indicate population density. And this is then basically intersected with the flooded areas so as to determine the exposed population. So that's what you see here in yellow and reddish tones. We have a legend here. So that refers to the density of the exposed population. We have information about land cover. So that's a land cover product that is again in the Google data catalog. It's a MODIS product. And this will tell us basically cropland and urban areas. And we can use that information to see again, what intersects with the flood mask. So affected cropland would be this. Affected, urban areas are quite small here, what are classified as urban areas. Based on these layers, the script is doing some calculations. These are estimates. So really, these are rough estimates. Based on the imagery, and again, ground truthing is critical there, but it's providing an estimate. If you want to see what basically the script has taken as data, you can find some details here. We've indicated a relatively long period after the flood, so there are several images, and to a certain extent, it will use all of them. Usually, it's good to narrow that down. So if you know when the satellite has passed over the location, it's useful to try to narrow the after down. Let me try to do that a bit. So I'm just changing that period so that we have a few elements. And I can see from the file name, it's 2020-09. And here's 22 and 29. So we see that there's quite some imagery on 22. So I will just basically go back and do that again. So the after flood period is really narrowed down, and we use imagery from that time. But as you can see, that imagery from that time was only a part of the region, not the entire one. So that is, if we provide longer periods of time, then it will combine data from different days. So the other one was on 29. So I'm just gonna use this, and this should give us the other part of the area. So that's a way to really use the image for a specific date. But if after the flood period is longer, it will simply combine different tiles and also bring results, of course. If you select a period of time where there is no data available, so the satellite did not pass over the location, let me try to do that, you will get an error. This is typically something that looks like this, saying, yeah, there's no data. And then the rest is also failing. If you get this type of error, do change the time frame. So try to find the time when there's data. You will get the same error when you change to descending here, because there will be no data. All right, so let's go back to those days at the end of September last year. We run this, and then we will have the flood mask, which you can then export. So under tasks, Google Earth Engine allows us to export some of the data, the flood extent as a vector, the flood extent as a raster, and the exposed population as a raster file. And once you export that, you can save it to your Google Drive and download it to your desktop. And then you can continue working in QGIS with the data to develop a map or to overlay it with other information. So that's the process. That's what this recommended practice allows you to do. Again, just to underline the differences, data availability. So it takes a bit of time until data is available here, which, depending on your use case, might or might not be a problem. But just be aware of that. So if it's really rapid mapping, it might be worthwhile to look at the previous recommended practice that Victor presented. But again, this one can be easily then exported to continue the work on a desktop JS tool. All right, are there any questions on this one? I will just go back to the presentation to see if we had some other slides where we did have just to basically show you some. As we mentioned, you can export these things and create a map and combine with other data sources. I will show QGIS a bit later on, but the idea is that this can indeed then be used for map creation. So this was the first part of this afternoon session on the recommended practices. Are there any questions before we move on to the next one?
Okay, this is God's time. Thank you very much, Radu, for your presentation and then the other team members. I had the link to the page for the recommended for those who would like to go to the location where this is residing, so that you can actually practice this on your own. This has really been simplified in such a way that you don't really need to be 100% highly skilled IT person. As long as you can through Google Earth Engine, then you should be able to run the script. The script has already been written, it has been tested, and it has been debugged. It's just to parameters to change, which very few. But the link is in the chat box. You should just go straight to where the recommended practice is after the. Thank you.
Thanks, Godstam. Yeah, that's very useful to have there. And indeed, we're also always interested in feedback. So if you use this for developing a product, we would, of course, like to know that this has been used. So that's also something for us useful to know. We want to know if the things we work on are useful to our stakeholders. And we always like to see maps that have been created using this. Are there any other questions? I see one hand up. Now I don't see that hand up anymore. Okay, so then we'll continue for a bit with, well, basically opening up from this step-by-step part to slightly, more global web-based systems, while also thinking a bit about how to use this and yeah, basically about knowledge management. And I would hope that we also have a bit of, well, the discussion after the following set of slides. So the second part on global web-based applications for flood and drought monitoring and the integration into desktop GIS, which is obviously a very long title, has the objective to indeed just highlight a couple of systems that have been emerging over the past years. We have seen GLOFAS, and I'll briefly speak about GLOFAS. It also has the objective of thinking a bit, how to integrate online and offline sources into desktop GIS. For some of you, this might be very straightforward, but I would like just to underline how, to a certain extent, straightforward it has become to combine data sources that are available online through standards such as web map services or GeoJSON, which is what a lot of the data files on the Grid 3 platform in Nigeria are available in. And I just want to underline that a bit. I will start by showing the UN Spider Knowledge Portal, showing different parts of the knowledge portal. So now we've kind of looked at something very specific, the recommended practices. We'll now zoom out a bit and we'll take a larger look, and I will also try to reflect a bit on how data sources, software, methodologies can be integrated into a knowledge management process and where we go from here, and maybe that gives some food for thought and the discussion later on. So what we do at UN Spider in terms of knowledge management is a bit visualized here, and we have different vehicles to do that. I will focus a bit on the knowledge portal, but as Juan Carlos also mentioned in his presentation yesterday, we of course do technical advisory support through different types of missions, and they always have a knowledge management component. I will focus a bit more on the portal because we're speaking about such systems now. And on the portal, and these different tiles that you see here correspond a bit to what's commonly referred to as the knowledge management cycle. We try to facilitate discovery and access of space-based information. So as you will see in a second, we categorize different data sources from third parties. So we don't have our own data. We also don't have our own satellite imagery, but we try to see what is available and how could that be used in disaster management. And then we will categorize, we will tag, we will mark up data such a way that it makes it easier to find if you have a specific use case like flood management. So we assess and organize, with other words. Then we highlight how to create information products. So that is indeed what the recommended practices are doing, but we also highlight how to reuse information products, how to reuse global web-based GIS systems, which I will mention in a bit, that indeed provide interesting insights already. So they go beyond providing the mere data, but they really provide to a certain extent information and knowledge. And we try to encourage sharing, which we also do, of course, through events like this one. So the knowledge portal, you'll find that at unspider.org, and I will just switch to my browser and basically walk you through a couple of the pages that we have here. So this is the front page of the knowledge portal. On the front page, you will find towards the bottom, but also in the slideshow, news articles that cover recent developments in the area of the use of space-based information for disaster management. We also have an events calendar where we try to see what the larger community is doing. So these are not our events, not all of them, some of them are, of course. It's more, what is the community doing? You will also find online training. So every time there's a new online course, a new MOOC, we will try to have that here. In the slideshow, you also see that we have a news item on our event. on the expert meeting already up there. And as we move to the right in the menu, we see space application. This part is providing background information on satellite technology. It's providing information on mechanisms that have been set up by the space community to support disaster response efforts. And it's providing some other background information. So if you are relatively new to space technology, to Earth observation, remote sensing, this might be a place to just have a look around to see what's actually, what's available, what's being done with satellite technology, what emergency mechanisms exist. You will find the International Charter Space and Major Disasters under this menu item. Gottstein spoke about that a bit in his presentation. So all of this is here. This has the objective of providing background information. As we move to the right, we will have some information on disaster management. So that's this part on disaster risk management, early warning systems, but also on the different natural hazards, as well as on what the UN is doing in this area of work and the Sendai framework, which, as I mentioned, is an important international framework for disaster risk reduction. Links and resources, I will click into this one because that indeed also came up yesterday. There were questions about data sources and so on. So links and resources have a couple of very useful segments. The data application of the month, just to show you that, is usually a relatively general piece of content. So on different topics, let's see if we have something on floods. So we recently did one on machine learning for flood detection, but we also did one on oil spill mapping some time ago. That is kind of a very easy introduction to the topic, showing what space-based information can do to support users, disaster management stakeholders in addressing these hazards, what data sets are available, what literature is available. So that's really a page that is useful to go through and read up on the different application examples. We then have pages that are more like mini databases in the system. So data sources, what you will find in the data sources are indeed data sources from third-party providers, so they're not ours, but we are trying to categorize them. One way we do that is we look at which hazard, do they support. So which if you wanted to indeed do flood mapping or drought monitoring, what data sets would be useful for that? If you have specific data type in mind, you can select that here. Specific file type, you can select that here. So if I'm looking for shape files for whatever reason, or KML or some other data format, we try to basically bring that together and categorize data sources so that it's easier to find them. Yeah, here's just some examples. So this would be active fire data. And indicating the publisher of the data, the format of the data, but it's already undergone a certain filtering process. We're trying to make sure this includes only data that is relevant to disaster management. It's not any data. Sometimes, of course, population data, for instance, is relatively general, but of course important for what we do. So that would also be included. But just to say that we're trying to cut through the noise a bit to avoid or help people not having to go to a search engine and search the World Wide Web before they find something, but actually, filtering a bit through. So that's under data sources. And if we move on to GIS and remote sensing software, we have a similar database for that. Again, you can set some search criteria, and it will provide you with a list of software that can be used. So that's same logic. If there's a tutorial or if we have used it in in a recommended practice. Let me see if I can find Snap, for instance. That's the Sentinel application platform, which we have used in a couple of recommended practices. You would see also directly the recommended practices where we have used that. So that's something that then allows you to just continue. Or if you are on the recommended practice, you want to learn more about the software, you will be able to click on the software name. It takes you to this page. So that's to basically cover all aspects of this work. And one other page that I would like to highlight under links and resources is the external online training opportunities. So these are online trainings provided by a wide range of organizations, NASA, but also the European Copernicus program and others. They also include sometimes MOOCs that are published on platforms like Coursera, for instance. So we try to keep a track on top of what's being published so that users can then, again, easily find it. If you say, well, I have a bit of time, or I'm actually quite interested to do, a longer online course, something that helps me understand better how I can use satellite technologies for flood mapping. Basically, you select floods here and you see what we have in the system, or if there's a specific satellite. So we spoke about Sentinel-1. So you can see if we have something that is directly related to that. Under advisory support, you will find some background information about the advisory support that we provide, as well as the page on recommended practices. So here, if I go on the recommended practices page, this will list all recommended practices. If you scroll down, you can browse them, but you can also filter them. So now we've looked at floods, we could say, well, let's look at what we have on floods. And there are a couple that are addressing floods. So that's also in here. And then you can click through and you get to the pages that I showed earlier. So if I click on the one with for flood damage mapping and damage assessment using Sentinel-1 SAR data, I get to this page. So that's under advisory support, recommended practices, and Godstam kindly posted the link in the chat. We have networks, so some information about some of the networks we're part of, some of the projects, such as the SPEAR initiative, which was presented yesterday as well. And the news and events will take you to the news items that you also find on the front page. So this, very quickly, is the knowledge portal. Again, there are different parts to it, some more background information, some are more meant to help users identify the resources that they need. And yeah, I will now move on from that. Here's just a slide with what I walked you through now, just in form of a slide. Again, what we try to systematically do is indeed have these filters on as many content items as possible. So if you're facing a certain hazard, this will allow finding resources quickly. The idea being, and that's something that I've mentioned earlier, and you've seen on Knowledge Portal, we try to show relevant data, relevant software, but also relevant methodologies, such as the recommended practices, because these all go hand in hand. And at the end of the day, you will need tutorials, methodologies to be able to use the data and actually develop information products. And of course, software is just as important. So as we've seen earlier, we do this for all phases of the disaster management cycle. So we address all phases, the data applications of the month, the recommended practices, the data sources, and so on. They're not looking only at emergency response, but also at other parts of the disaster management cycle. So the whole knowledge portal is meant to support the whole disaster management cycle. Okay, I will now move to showing you one or two systems. I'm not going to go into extreme detail on those systems, also because, of course, they're quite complex systems to a certain extent, and this will require more time. But I would like to underline that they are available, and I would just like to show them, and then I would like to show how to use the data also in a desktop GIS. So that will also go hand in hand with that. So GLOFAS, which you heard about earlier, is the Global Flood Awareness System. developed by the Joint Research Center, the European Commission, and it's freely accessible. You just need to create an account. You can get to the GLOFAS website here, create an account, and then start using it. It includes meteorological, hydrological data, of course, the information on flood thresholds and so on that we have briefly seen earlier and that I'll show in a bit. So the flood risk assessment. It's covering riverine floods, not necessarily coastal flooding or flash floods. And it includes an experimental rapid flood mapping layer with a resolution of 1 kilometer. So based on the maximum return period threshold exceeded by the ensemble mean river discharge, the system will look into a catalog of flood events and then indicate basically the potential flood mapping layer. So what I'll show you in a bit, and I would also strongly suggest, and that's something that is valid for all systems, to look at the documentation, because it's always worthwhile to understand the processing, which models are used, and so on. Of course, systems, you click on the buttons, they give you results, but the question is what's happening under the hood and what's happening, how do we get to those results. So for GLOFAS, there are different types of observations that go into the modeling. So of course, meteorological. Sorry, I just okay. So different observations that go into the system, which includes satellite and in situ observations. So I think this integrated approach is quite important also to underline some static data sets, and then meteorological forecasts from the European Center for Medium Weather Forecasts, and also from other entities, federal meteorological modeling then happening using the this flood model, which is also openly accessible. And at the end, this goes into the web interface, and that's what I just would like to briefly show. So I will just go to the GLOFAS, the GLOFAS map viewer. Actually, let me show you the main page first, so that you know how to get here. So if you go to globalfloods.eu, this will be the interface, and it's possible to sign up here. I'm not signed in, but in theory, that is not, you wouldn't be signed in. You can create an account, sign up, and then you can go to the map viewer. There's more information under general information and under technical information. So again, I think it's very well documented. The system has a lot of documentation that is worthwhile going through. To see the system in action, there's a map viewer. Sorry, this is the wrong map viewer. There we go. And this one will allow you to basically overlay different data sets. Just to take one very simple one, accumulated precipitation, just to give you an idea, under meteorological data. And then under hydrological data, we have the different flood-related data sets. So flood summaries. And this is looking ahead. So it's looking, I think it's the next 10 days. And you can see, if I go to this area, we could also, well, let's actually do that. We can go back in time. So we can here go back to 2020 and maybe look at the same kind of period of time that we looked at for the recommended practices. So this is now the forecast for, let me just remove that. The flood summary for the next 1 to 3 days on the 1st of September 2020, and it indicates the likelihood of exceeding a certain return period. So that's what the system is showing in a nutshell. As I said, you can also then go into flood risk and activate two layers, which are experimental, the rapid flood mapping and the rapid impact assessment. So the rapid flood mapping will then take the forecast, take the database of flood events, and give an estimate of how they could play out with a certain resolution. You can find information about all the layers by clicking on the small eye icon here, and that will then basically explain what that layer is doing. So again, this is very transparent and helpful, of course. So that's for flood forecasting with GloFAS. I will show in a second how to get that data into QGIS. Another system that is also providing such a map viewer is the Operation Flood Forecasting and Alerts in West Africa, Project FANFA. It was mentioned earlier today. And FANFA has a number of hydrological models that can be run. It also integrates water levels from altimetry data that comes from Sentinel-3. So that's the input of the satellite data. But of course, there's meteorological data. And FANFA basically is accessible at this address. If we go to the page, which I've opened up here, you would see some information about the project. And then under forecast, there's the interactive visualization portal. There's a user guide, there are YouTube videos. So all of these systems are very well documented. It's really easy to start looking into them, to seeing what they can do, what they can't do. And here again, we have severity levels based on the likelihood of a certain return period that can be activated. We also have the option to change the model. And again, there's documentation about the different models used. So there's, for instance, this model that is for the Niger River basin, and then there's one for West Africa, one that is global. Again, I'm not going into details, but I just want to point out that these systems which are doing the processing, which do a bit of the, which do the hydrological modeling and then provide the information, have become quite easily accessible. And again, they don't require you to download the data or to run the things, and might help to get a first glance. But I also would like again to underline that, of course, these are not necessarily, it's not the absolute truth. So all of this is something that needs to be combined and needs to be understood in a local context. Right. So I'm just moving on to, we'll skip this one since we're a bit running out of time. This is a system that is also providing forecast using, again, data from the European Center for Medium Range Weather Forecasting. And they can also be accessed freely online with a forecast and indicating the likely return period. The other systems, we have seen radar remote sensing. The other systems that are using other technologies, so for instance, optical imagery and data rather than radar, to calculate the flood extent, to estimate the flood extent, and they're using certain characteristics, spectral signatures of water. One of these, and there's a link in here, I won't go into detail, is basically this Real Earth platform, as it's called, that is taking data from NASA missions and basically indicating flood extents. There are advantages and limitations, but it's another online system that is global and actually near real time. So it's probably useful to be aware of that. As we move to drought, just to underline that, of course, there are different drought types we know of: meteorological, agricultural, hydrological. and there are different parameters used for that. So this is, of course, very, very general, but just to say that on the knowledge portal, you will also find recommended practices that support drought monitoring. This is the output of the recommended practice using the standardized vegetation index, which is available in R and in Python. And we also have a Google Earth Engine version of that now. And that is something that allows you to monitor conditions compared to basically the average over a certain period of time to see if the situation or the vegetation on a certain day of the year, is healthier or not as healthy as usually. Again, all of this is very much explained on the knowledge portal and in detail, and it is something that can be run for any area, but of course there are advantages and limitations that we have also listed on the knowledge portal. As I mentioned, this is the SVI. There's also one that uses the vegetation condition index, and more recently we've developed one with the standardized precipitation index on Google Earth Engine. There are also global systems. So again, the European Copernicus program is putting out the Global Drought Observatory. It's also work done at the Joint Research Center of the European Commission, which is a system that's, again, global. And if I show that map viewer quickly, looks like this. And there are also different indices that and risk indicators that are basically running in the background to establish the drought risk in this case. It's called the risk for drought impact for agriculture. And there's extensive documentation that explains the methodology and the processing behind, but there's also a system that's readily available. It's, again, for a quick look at the situation, quite useful. Also, for more than that, they also produce drought reports for specific drought events or on regular basis, and also provide access to a wide range of data sources. Some other platforms you might want to look at if you're interested in drought are listed here. What I would just like to show quickly is the idea of integrating all of this into QGIS. So a very basic standard for getting georeferenced data and maps over the internet is the web map service, which is something that allows a user to plug into an online system easily and get the data into a desktop tool. So I will just briefly show you what that would look like on QGIS with GloFAS. So I hope you can now see my QGIS window. I'm just zooming out a bit. Right, so here there's a lot of data. What I would like to point you to is the data from GloFAS. So this is what we've earlier seen in the map viewer. And since GloFAS is offering an endpoint for web map service, it's possible to integrate the data into QGIS as well. And the way to do that is to, first of all, find the web map service link, which I have included on the slides, I believe, and then to bring it into the system. So on QGIS, there's the data source manager, and you will see here different options for web map services, web feature services, some other online services. And this can then be used to bring the data in. We earlier saw some examples of GeoServer and other systems providing data that is then queried with QGIS. Here we're looking at the web map service. We define it. So to define a web map service, you need a URL, which you can easily find. Once we have put that in, we don't need anything else. We just connect to it, and we get a set of layers that we can then bring into the system. So I will just take the precipitation layer that I opened earlier, and I just put that into the system. And you can see this appearing now on the desktop GIS. So this is literally data that is brought in from GloFAS right now. And like that, we can build up, we can bring in different data sources. We can bring in, of course, CSV file from the computer, the global sources, maybe something that's done locally on the system, and have all of this in a system, in a tool like QGIS or ArcGIS. And just to finish, if we wanted now to do flood mapping with the recommended practice that I showed earlier with Google Earth Engine, we could do that inside QGIS. So QGIS has a number of plugins which allow to extend the functionalities. QGIS is also working with Python quite well. So all of this can then be brought together. So we can really tap into all of these resources. So if I open the Python editor, this is a script that is basically going to Google Earth Engine, doing what we saw earlier on Google Earth Engine and getting the data back. So if I do this now, let me just untick the other layers. Then I will get, for a certain area, I will get some information. So here, up here, in its KB state, I will get a flood layer. And this is the output of the recommended practice that I showed earlier on Google Earth Engine, where we can do that straight away out of QGIS. And that allows us to really combine, integrate different data sources, and build a bit of a system that helps us keep an overview here. All right, so with that, I'm basically, and this is what I just mentioned on the different data sources. I'll just finish with this slide, which is from a book on knowledge management, and it's become a bit of an established visual, this knowledge management ladder. The idea is that what we're aiming for is to move, up a bit from data. We try to provide meaning to have information, using that in the context that we know, where we have experiences, where we know what to expect. We slowly build up knowledge, and with the necessary motivation, with the application opportunities, we develop actions and move up this this knowledge management ladder. But it requires two things. One is the operational part, the other one is the strategic part. So I think we spoke about capacity building, we spoke about all of these issues, and it's just important to have a bit of strategic direction, to also build up the capacities, as it is to have the access to the data to build up the systems. And with that, I'd like to thank you. And if you have any questions, please put them in the chat or raise your hand and we'll address them.
Thank you very much, Radu. This has been a very thorough explanation of some of the content of the portal. Indeed, I would like to kindly open the floor for comments or suggestions. So it seems everybody is totally clear on these topics, but I think that looking at some of the procedures that were shown by Ingrid and Victor and by you to process satellite imagery, one of the issues that we could consider is definitely doing a training that would also include some of the basics, maybe going over the original recommended practice with the SNAP software, where we have all of the procedures there, so that people can then understand what is the advantage of doing the procedures in the cloud, but also the implications of just then using faster procedures in that sense. So I think maybe in the near future we could organize a training course along with NASRDA and the Center for Space Science and Technology Education, if this would be something that the participants would be interested in. So with this, I open the floor for comments or suggestions.
Well, good afternoon.
Good afternoon.
Yeah, thank you. I really appreciate all the the way the presentation goes, it was well, because it's meant to touch several aspects of what is available, and that has been done very well. It opens up a lot of new ways of doing so many things and available sources. It's now left to us to really, just as I said the other time, to really put everything together and not limit ourselves to a particular way of carrying out all these predictions and knowing what is going on here and there. But as I said, they need to be domesticated. The basic underlying knowledge about it need to be taught. People need to be given the right orientation in order to be able to pick it up and know what they are doing if they are clicking any button, for example. So it still means that the issue of capacity building, as you said, is very important. But what has been demonstrated here is not for you to be able to know it immediately, but just for you to know that they exist. You can make use of those things out there, which is very good. It's very important. So it's now time to start the real work from the partners, especially in Nigeria. Thank you.
Yes, thank you very much for your comments. I fully agree with you that there's a need for more in-depth training, not only of the procedures, but also the theory behind. In that sense, definitely we'll work on that. I also think that we also have to be able to take some of the knowledge, maybe not necessarily at the level of processing satellite imagery, but bringing a little bit of the knowledge on how space-based information can be used in disaster management to the state and to the more local levels. And probably there, I think the interest might be also on the use of geo-viewers. You mentioned this morning, for example, that you're working and then you're facilitating the use of tablets to see the products that are being developed as part of the MeetFast project that you're developing. And I think that the use of tablets is something that we definitely need to encourage, at least to facilitate the visualization of the information that is generated at the national level.
Yeah, you're right. Yeah. So it's a lot of cooperation, collaboration, working together to get it. But they make a lot of difference in terms of making it faster and getting the information to the right people and ensuring that there's reduction actually in all these disasters as they come around. Yeah, that's good.
Right, definitely. I see that there's a request to have the presentations. Yes, we will, of course, put all the presentations available in the UN Spider Knowledge portal, and we'll send you an email with all the information as well as a summary of the expert meeting. And we look forward to, as I say, seeing how we can build capacities of people at different levels together with partners in Nigeria. We'd love to be able to contribute our little inputs there, whatever we can do, because I know that the real capacity building efforts have to be carried out inside Nigeria with institutions, but we look forward to our contributions. Having said that, if there are no more comments or suggestions, then I would like to close the session for today and invite you tomorrow to the next session of this very interesting expert meeting. And I would like to thank you for your participation. And I wish you a very good night. And I would like to thank Radu and our colleagues Ingrid and Victor for this technical presentation this afternoon. Gostam, I don't know if you have any comments or suggestions.
Thank you very much. Just to thank all the presenters as well as the participants. The number of participants had gone up to 51% as I started, and So it shows a lot of interest. What I would say, just in line with what Dr. Agbaje and Yuan has said, we will definitely work out a mechanism where we can run hands-on training on all these recommended practices. We've done this for a couple of organizations. We plan to do that for NEMA sometime either this month or next month. So we will be organizing series of these trainings that will be hands-on based. They will be perhaps 1 week. So there will be time for participants to be able to run through these processes on their own, make mistakes, get corrected, and then move on. And then also for a much more robust training scheme, of course, we can partner with our center, the African Regional Center for Space-Based Education and Language. So we can, of course, work them, organize a much more robust. Tomorrow again, we are starting by 11 o'clock. Please try and log in before 11 so that you can be allowed into the platform early enough. We have a couple of presentations tomorrow, and we'll be rounding up tomorrow as well. So if there are suggestions on what you think we can do better as a country with regards to the use of space-based technology for disaster management, please think over it and bring this up tomorrow. We'll have a lot of time tomorrow for just conversation. If there is no synergy between the MDAs as we currently have it, if there are reasons for that, please let us know. If there are ways that you think the synergy can be improved, please let us know. So tomorrow we are going to be dealing with solutions and solutions. Thank you very much.
Thank you very much, Godstam, and thanks everyone for attending this very interesting session, and we look forward to seeing you tomorrow. I wish you a very nice evening on behalf of all of us. Bye.
Okay, bye.
Bye.
Have a nice afternoon.
Bye-bye.
Have a nice evening. Bye-bye.
Bye-bye. Nice.
Bye.
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 Bye-bye, Juan.
Bye. See you tomorrow.
Take care. See you tomorrow. All the best.